The Time Value of Money, Part 1. The purpose of this section is to develop the mathematical relationships for the time value of money. Because money can earn interest, the value of $1 million today is not equal to the value of $1 million 10 years from today. If given the choice between $1 million today and $1 million in 10 years, you would choose it today even if you didn't plan to spend the money for 10 years, because you could take the $1 million, receive it today, invest it essentially risk-free by buying U.S. Treasury bills, and 10 years later you would have more than $1 million. Therefore, money is said to have time value. We begin with the basic formula for the future value of a present amount. And the future value, n periods from today, of a given present value amount today at an interest rate of r per period can be computed by taking the present value amount and multiplying it by 1 plus the interest rate and then raising that to the n power. That gives us the future value. So FV is future value, PV is present value, R is interest rate per period, which we put in as a decimal when we do the algebraic calculation, N is the number of time periods. Notice I'm defining interest rate per period and number of time periods. In our initial examples, it'll always be interest rate per year and then number of years, but that's going to change. And we'll also use this formula to handle problems where interest is compounded semi-annually or quarterly or monthly. Let's look at an example. If you invest $10,000 today into an account that pays an interest rate of 10% per year, what will be the future value of the account 30 years from today? So I show a time diagram here where at time 0 today, $10,000 is placed into an account. It's going to earn interest at 10% per year, and we want to know the future value in 30 years. So we use the equation for the future value of a present amount. We plug in the $10,000. Notice we take the 10% interest rate, we make it 0.10 and add it to 1 to get 1.10, raise it to the 30th power, and we get a future value of $174,494.02. Now, if you have the Hewlett-Packard HP10B2 calculator, I'm going to be giving throughout these sections instructions on how to solve the problems both algebraically and then with the HP10B calculator. You're going to begin by pressing gold Clairol. Now, there's some debate on whether the key is really gold. The G in that yellow goldish box there stands for gold. But people tell me that it's more of an orangish color, but regardless, I'm going to call it gold because I'm used to doing that, so please bear with me on that. So begin by finding that key. It's simply a key over in the middle of the calculator towards the left side, and it's simply colored gold or orange. Press that key and then find the See All key. It's the Clear All key. This calculator has continuous memory. Turning it off does not clear it. And if you've used these keys across the top of your calculator the last time you used the calculator and those numbers are still there, well, we'll be overriding these three and then solving for future value, but there might be an entry there under payment. And if we don't press gold clear all first, that number will still be there unless we hit 0 and enter it for payment, and it will mess up our calculation. So get in the habit of pressing gold clear all. That will zero out everything that was there from any previous calculations. So put in 30 and press N after pressing gold clear all. 10 IP here. Now notice we don't enter as a decimal when we're using the HP calculator. We put it in as a percentage. So you got to be careful. Use the algebra, put in the decimal. Using the HP calculator, put it in as a percentage. Put in the 10,000 as the present value. You don't type a comma. I just put it there to make it easier to follow the numbers. And it doesn't matter which order you put these three entries in. Lastly, you'll press future value and you'll get the solution. You'll get it as a negative number. Don't let that bother you, but let's start paying attention to that because we're going to have to anticipate that later. The calculator takes into account the direction of cash flows. And it's assuming that if you put 10,000 into account, making it positive, you could then take out the future value amount that we get. So that's why you have the different signs there. And it's just you don't have to worry about the signs in an absolute sense, just in a general sense. If a present value amount goes in as positive, you'll get a negative answer here. We could have entered the 10,000 as a negative answer, and we would have gotten a positive future value. Let's talk about the compounding of interest. When computing the future value of a given present amount, the future value equation that we're using here assumes interest is compounded. It assumes the compounding of interest. Compounding the interest simply means that when interest is paid in one period, it will earn interest in the next period as long as you haven't withdrawn that interest. And that's what we mean by compounding of interest. You don't need to worry about it because the formula takes that into account. The interest rate used to compute a future value is often referred to as a compound interest rate. To illustrate the power of compounding, let's go back to the last example and let's compute the future value at interest rates of 8% and 12%. We've already done 10%. So we take the same calculation and we put in future value equal 10,000 times 1.08 to the 30th, and we get $100,626.57. At 12%, we would get $299,599.22. If we compare these on the graph, these are all three results. At 10%, which was the original example, we got $174,494. At 8%, we got $100,627, and we would guess that's intuitive that we would get a lower future value. But the point I want to make is look how much higher the future value is at 12%. Over a long time period, such as 20, 30, or 40 years, even greater, even relatively small differences in interest rates can make quite a difference in the future value. Going from 8% to 12% over a 30-year time period results in a future value that's almost 3 times the size you would have at 8%. That is the power of compounding. Okay, now we're going to do the reverse calculation, and we're going to solve for the present value of a future amount. And it's easily obtained by simply taking the previous equation for the future value of a present amount and solving for the present value. And we get present value is equal to future value times 1 over 1 plus r to the n. Or we can drop the brackets, move the future value into the numerator, and we'll usually write it this way: future value, present value equal future value divided by 1 plus r to the n. Let's do an example. You expect to receive a $50,000 payment 20 years from today. At an interest rate of 8%, what is the present value of this future payment? Well, here's our time diagram. Out here in the future, 20 years from today, we have an expected future payment of $50,000. The interest rate is 8%. We want to compute present value. So we take the future value and divide by 1 plus r to the n. The future value is 50,000. Again, we put the interest rate in as a decimal. So we take 1.08 to the 20th in the denominator, divide that into 50,000, and we get a present value of $10,727.41. On the calculator, again, we begin by pressing gold clear all to zero out those keys across the top there. We would press 20, then N, 8, again, put it in as a percentage, not as a decimal when you do the calculator solution, I per year, press 50,000 and enter it as a future value. Again, you can do those three in any order, and then last, you want to press the present value key. And you'll get a negative answer. Again, in a relative sense, the calculator takes into account the signs of the cash flows. If you're going to receive $50,000 in the future, you would have to invest an amount to date in order to get that. To illustrate the relationships between present values and interest rates, let's go back to the previous example and compute the present value at interest rates of 10% and 12%. We just did 8%. At 10%, we would get $7,432.18. And at 12%, we would get $5,183.34. At 8%, if you'll recall, we got $10,727.41. So we see that as the interest rate increased from 8% to 10% to 12%, the present value went from 10,000 something to 7,432 to 5,183, and we find that present values are inversely related to interest rates. As interest rates go up, present values will fall, and vice versa. That's an important relationship to keep in mind throughout this course. The process of computing the present value of a given future value amount is known as discounting. It's not a marketing term. There's nothing on sale here. But when we compute present value in finance, we call that discounting. The interest rate used to compute the present value is referred to as a discount rate, and we'll use that term a lot. You'll hear that term a lot in the field of finance. It simply means interest rate used to compute a present value. Okay, what if we have multiple future value amounts? Well, the present value of multiple future values can be computed by simply summing the present values of the individual future value amounts. In other words, present values are additive. So if we had n cash flows out into the future, year 1, year 2, year 3, and any number in between out to year n, simply take the present value of each one and add them together. Let's do an example. Compute the present value of $1,000 received 1 year from today, $1,400 2 years from today, $1,800 3 years from today, and $2,000 4 years from today, and an interest rate of 6%. Well, here's my time diagram showing the $1,000 1 year from today, $1,400 2 years from today, and so forth. If we want the present value at time 0, I simply take the 1,000 over 1.06 to the 1 power. I can drop the parentheses in the 1. $1,400 over 1.06 squared. Remember, put the interest rate in as a decimal. 1,800 over 1.06 cubed, and then add to that 2,000 over 1.06 to the 4th. And if you took the time to do that algebraically on your calculator, you'll get $5,284.89. But our calculator has a very interesting algorithm that allows us to calculate this quite quickly. Let's begin with the gold Clairol key, and we're going to use a key known as the CF sub j key. So locate that. Now, whenever you're going to use the CF sub j key, you must enter year 0 by itself even when it doesn't exist. And in this problem here, there is no year 0. The first cash flow is in year 1. We have to tell the calculator that the cash flow in year 0 is 0, and then press CF sub j. You must do that every time. If there is a cash flow, and later in the course we'll have cash flows there, we will enter those cash flows. They're often negative at time 0. Then we just take our time and enter the cash flows. 1,000 CF sub j, 1,400 CF sub j, 1,800 CF sub j, 2,000 CF sub j. So all we've done here is we've described to the calculator what our time diagram looks like. Next, we press 6 and hit I per year. And then as our last step, we press gold NPV. NPV stands for net present value, and we're going to be covering that later in the course. But we can go ahead and use that ahead of time because it's a very powerful function. It's simply taking the present value of these 4 cash flows and adding them together to get the present value. And this ends Time Value of Money, Part 1.